Hydraulics. Mechanical systems on aircraft convert pilot muscle power into forces required to operate aircraft systems and various services, for example flight controls. On small aircraft this may not be a problem, but with large or fast-moving aircraft, forces required may be very large and high pressure and large flow may be required. The use of hydraulic power overcomes this problem. The hydraulic power provided is determined by two factors: system pressure and volume flow. A basic hydraulic system may be either active or passive. In an active system, this is pressurized by a pressure pump, for example engine-driven or air-driven. In a passive system, this is not pressurized by a pressure pump. Hand or foot-operated pumps are used. Basic hydraulic system schematic. The system starts with the hydraulic tank or reservoir, which is a storage of fluid. A pump draws from the reservoir and is used to pressurize the system. Fluid flows to a selector valve, which can be diverted to supply fluid to either side of the actuator. The hydraulic pressure is converted into mechanical energy. In its present state, this jack is hydraulically locked, as the selector valve is closing off both the inlet and outlet. Hydromechanical principles. Hydraulic systems transmit power by moving a column of incompressible fluid from one place to another. Fluids, either gases or liquids, transmit pressure. Pressure is equal to force over area. Pascal's law describes one of the fundamental principles of hydraulic transmission of pressure. It states that the pressure in an enclosed vessel acts at right angles to the walls enclosing the fluid, and that the pressure is transmitted equally and undiminished to all parts of the vessel. Pascal's law can be illustrated using a Bramah press. The Bramah Press. A force of 10 newtons acts over 1 centimetre squared at point A. The pressure is therefore 10 newtons per centimetre squared. The area at point B is 10 centimetres squared and the pressure exerted is 10 newtons per square centimetre from Pascal's law. Therefore the force that can be supported at point B is 100 newtons. A piston acting at A, 2 centimetres squared, is moved 5 centimetres. How much will the connecting piston move at B, 10 centimetres? A force of 10 newtons acts over 0.05 centimetres squared at point A. What is the pressure exerted at B, 0.5 centimetres squared? A piston acting at A, 10 centimetres squared, with a force of 20 newtons. How much force is there at the connecting piston at B, 2 centimetres squared? A piston acting at A, 10 millimetres squared, is moved 2 centimetres with a force of 100 newtons. How much will the connecting piston move at B, 100 millimetres squared, and what force will be produced? A piston acting at A, 2 centimetres squared, is moved 5 centimetres. How much will the connecting piston move at B, 10 centimetres squared? Area multiplied by distance equals area multiplied by distance. So, 2 multiplied by 5 equals 10 multiplied by the unknown distance. 2 multiplied by 5 is 10, divide by 10, equaling 1 centimetre. A force of 10 newtons acts over 0.05 centimetres squared at point A. What is the pressure exerted at B, 0.5 centimetres squared? Force over area equals force over area. 10 over 0.05 centimetres equals force over 0.5. 10 divided by 0.5 is 200, multiplied by 0.5 equals 100 newtons. A piston acting at A, 10 centimetres squared, with a force of 20 newtons exerts a force at B, 2 centimetres squared of. Force over area equals force over area. 20 over 10 equals force over 2. 20 divided by 10 is 2, multiplied by the 2 is 4 newtons. A piston acting at A, 10 millimetres squared, is moved 2 centimetres with a force of 100 newtons. How much will the connecting piston move at B, 100 millimetres squared, and what force will be produced? Area multiplied by distance equals area multiplied by distance. So 10 multiplied by 2 centimetres equals 100 times the unknown distance. 10 multiplied by 2 is 20. Divided by 100 is 0.2 centimetres. Input force multiplied by input distance equals output force multiplied by output distance. 100 newtons times 2 equals the output force times 0.2 centimetres. 200 divided by 0.2 equals 1000 newtons. Hydraulic fluid properties. Hydraulic fluids must have the following characteristics: good thermal stability, low emulsifying characteristics, corrosion resistance, high flash and fire points, good resistance to combustion, low compressibility, low volatility, low viscosity, and they should be compatible with other materials. This prevents deterioration of seals and gaskets. Types of hydraulic fluid. Vegetable oil, an example would be Lockheed 22, is straw or natural coloured, and the seal material is natural rubber. Mineral oil, for example DTD 585, is coloured red, and the seal material is synthetic rubber. Phosphate ester base synthetic fluids have a typical example of Skydrol. The colour is purple, and the seal material is butyl rubber or Teflon. Different types of fluid cannot be mixed. Synthetic fluids which have a high resistance to cavitation are used in modern hydraulic systems. Hydraulic fluids irritate eyes and skin, and special precautions are required. Passive system layout, a hand pump. Check valves, non-return valves, ensure that fluid does not return to the tank when the hand pump is operated. They also trap pressure in selected lines when the pump is at rest. If an external leak occurs, the fluid level in the reservoir drops. If an internal leak occurs, for example fluid seeps past a broken seal, the temperature of the fluid will rise. Active system layout. There's a tank which has two pipes in it. One pipe is higher than the other. The lower pipe serves as the emergency reserve. There's a certain distance between the top of the pipe and the base of the tank to prevent sludge from entering the system. Immediately after the tank is an emergency shut-off valve. In its current state, it's indicated in line, which means fluid is flowing into the system. There follows a pump. This is typically a constant flow pump. It's followed by a relief valve. When the pressure gets too high, fluid is passed back to the tank. If there should be a problem in the system and pressure were to rise, an automatic cut-off would open, allowing full flow return back to the tank. After the relief and cut-off valves, there's an accumulator. An accumulator is like a shock absorber. It contains fluid and gas within it with a dividing separator. It serves as a means of preventing surge in the system as an additional reserve of fluid. It's followed by a non-return valve, after which are the services, which can have reduced pressure, achieved by using pressure-reducing valves, for example to nose, wheel steering or brakes. Other systems would include flaps, slats, landing gear, which may require pressure-maintaining valves. You can also see at the bottom of the diagram another valve which is separating another system. Currently it's closed off. This would be opened if an engine had failed and services needed to receive fluid from the other system. Low pressure air supply from the engine is used to prevent cavitation of fluid in the tank. Active system components. The reservoir. This provides a reserve of fluid to compensate for minor leaks in the system. It allows for variation in fluid volume being returned, for example a jack being extended or retracted, or fluctuation in accumulator pressure. It allows for expansion of fluid due to an increase in temperature. It provides a head of pressure to prevent cavitation at the engine-driven pump. The reservoir can also be pressurised by bleed air from the engine. The emergency shut-off valve. This isolates the hydraulic system in the event of a system failure, for example a leak, an engine failure or a fire. Pumps can be constant volume, variable pressure, or constant pressure, variable volume. Constant volume pumps. Here are two examples. On the left is a spurred gear arrangement. The two gears work to take a volume of fluid and transfer it to the outlet of the pump. On the right is the slotted vane. As the pump turns, the slotted vane leaves its receptacle and isolates a volume of fluid and transfers it downstream. As the pump rotates, the slotted vane retracts back into its receptacle. The swash plate. This is an example of a variable volume, constant pressure pump. The whole thing is rotating. There's an inlet to which, in this case, there are 6 actuators, or jacks. As each jack moves, it draws in fluid, and as the swash plate turns, then that fluid is expelled downstream. The greater the throw of the jack, the more fluid will be displaced. Systems can be used to detect pressure downstream, and if there's a fall in pressure, the swash plate can be manually or automatically adjusted to increase the throw of the pistons, therefore sending out more fluid downstream. Active system components. Pumps. The constant volume pump delivers a constant volume of fluid at a particular engine speed. The lower the engine RPM, the lower the pump output. There is no internal control of the pump output, therefore a component external to the pump must be fitted to the control system pressure, for example an automatic cutout valve. Constant pressure pump. A volume of fluid delivered to the system is controlled from within the pump so that a constant system pressure is maintained, typically 3000 psi. If system pressure tends to be too high, the pump output is lowered. Non-return valve. This allows movement of fluid in one direction only. It's also known as a check valve. Pressure relief valve. This relieves excessive pressure by returning a small amount of fluid back to the reservoir. The accumulator. This stores fluid under pressure, prevents hydraulic hammering when placed adjacent to the automatic cutoff valve, is a means of energy storage, provides pressure to give impetus to components when they are selected, compensates for temporary drops in system pressure, provides fluid under pressure for emergency operation, for example wheel brakes, smooths out minor pressure fluctuations, and damps pressure surges in the system. The accumulator has a gas section and a hydraulic fluid section. The gas system may be pre-charged to a specific psi. If the system pre-charge is 1500 psi, and then an electric pump is started to operate the system at 3000 psi, then the separator in the accumulator will be displaced by the hydraulic pressure until the gas section pressure gauge reaches 3000 psi. Pressure reducing valves. These reduce system pressure to that required for a particular service. Thermal relief valve. This is fitted in a closed circuit to relieve excess pressure caused by thermal expansion of hydraulic fluid. It's sensitive to pressure, not temperature. Full flow relief valve. This allows full fluid flow to return to the reservoir. It's fitted to cater for the failure of the automatic cutoff valve or constant pressure pump sticking at full stroke. Restrictor valve. Allows restricted flow in one direction and full flow in the other. Selector valve controls selection of various services, may be fitted with a neutral selection so that a hydraulic lock may be created, for example a flap circuit. Shuttle valve allows 2 alternate sources of pressure to supply a service, for example normal and emergency supply. Shuttle valves switch hydraulically operated units to the most appropriate pressure supply. They supply an operating unit with the most appropriate system pressure. Pressure maintaining valves. These ensure priority of the services upstream of their position regardless of the needs of the services downstream. For example, speed brakes and flying controls take precedence over flaps and landing gear. It's sometimes called a priority valve. Actuators, or jacks, convert hydraulic pressure to mechanical energy. They can be linear or rotary. Piston actuators may be single-acting, hydraulic pressure is on one side, spring pressure is on the other, or double-acting differential area, or double-acting balanced area. The pressure line. This carries fluid under pressure and is usually made of steel. The return line returns fluid to the reservoir and is typically made of aluminium alloy. Case drain lines and fluid coolers. Pumps and actuators have case drain lines which carry fluid to the return. Heat exchangers are normally fitted in the return line. The temperature is also measured here. A hydraulic motor. This converts fluid pressure into rotary mechanical energy in order to drive an integral hydraulic pump. It may be used to drive a power transfer unit, PTU, which enables power to be transferred to another hydraulic system without transferring fluid. There are two main types of hydraulic systems. Self-idling, the pump is capable of maintaining system pressure from within, i.e. constant pressure variable volume pump. And non-self-idling, the pump delivers a constant volume of fluid and another component is fitted to maintain pressure, i.e. the automatic cutter valve. Some systems use two pumps for redundancy. If one fails, the other will still provide fluid flow, but at half the normal rate. Operating times of services will be doubled, but system pressure is still maintained. The ram air turbine. This provides electric and hydraulic power in an emergency. It operates through ram effect of slipstream air. Hydraulic fuses. A hydraulic fuse prevents total fluid loss in the case of a leaking hydraulic line. They are spring-loaded shuttle valves which close the hydraulic line if they detect a sudden increase in flow, such as a burst downstream, thereby preserving hydraulic fluid for the rest of the services. Hydraulic fuses are fitted to the brake system, leading edge flap slat extend retract lines, nose gear extend retract lines, and the thrust reverser pressure and return lines of the Boeing 737.